Okay, what's up, everyone? Welcome back. We're talking a little bit more today about inner products, in particular orthonormal bases, but we're going to touch down on something kind of cool. So the idea of this is as follows. This is our last little bit for this section. It's all about how do inner products interact with dualization. So recall, if we take a vector v and v, we can obtain here, let me zoom out a little tiny bit, give myself a little more space to write. A linear functional, let's call it phi in v prime via phi of, let's call it u, is equal to the inner product of u with v. That is, we can take a vector v and make a linear functional by just fixing it as the second argument in an inner product. This just works because in the first slot, an inner product is linear. That is, you can pull out scalars and you can split it up across sums. We've been working with this for the last couple days. Not too bad. Okay, so this motivates a very basic type of question. So the mapping that sends a v and v to the function, and I'll just put a dot there for the open argument, sends v to some portion of the dual space, to some portion of v prime. But how much? What linear functionals are of this form? That's our question. So if we take a vector v, we can map it to a linear functional. That is, we've got a map from v to v prime. And in fact, if you go and check, this map, I should be careful. This map is at least additive. Is this map homogeneous? Is it linear? Over a real vector space, yes. Over a complex vector space, not quite. We need to be careful because when you pull out a, sorry, I got a little cough. When you pull out a scalar from the second argument, you have to conjugate it. So it may not exactly be linear right there, but close. So what linear functionals are of this form? Let's do a quick example really fast. And notice that linear functionals that might not initially be written in this form sometimes are of this form. Here's one. But phi, that's a terrible phi. There we go. Here, I'll even say this. Be a linear map from F3 to F, which is just, to be clear, F3's dual space, though that looks kind of weird to write. Let it be defined by phi of x1, x2, x3 equals 2x1 minus 5x2 plus x3. Then, here's the claim. Phi of x, where x is x1, x2, x3, is equal to x inner product with v for v equal to what? Well, just think about it. It's 2 minus 5, 1, if this is the dot product. Just to be clear. So, and maybe it seems unclear to say the inner product without mentioning which one, but just looking at how the dot product works, you take first thing, x1, times first thing, 2, so you get 2x1, okay, and then you add it to second thing times second thing, minus 5x2, okay, and then third thing times third thing, 1x, oh, not x, I wrote it as a cubed right there, please forgive me. A little bit too early in the morning for Bryce, I guess. There we go. All right, sorry, that should be an x2 and an x3. But yeah, hopefully that seems clear. I think I said that. I'm sorry for writing it as squared and cubed. Indices getting mixed up with exponents. Oh no. But do you see what I mean? That this is a way of writing an inner product just a little bit hidden. But there are other things. For example, what about, say, phi in the dual space of the polynomials of degree n over the reals with phi of p equal to the integral from minus a, or how about just from a to b, any old a to b, of p of t, say, cosine of t dt. Cosine is not a polynomial. It's definitely not a polynomial of degree n for any n. So is this not an inner product, or is it? Let's answer the question. Let's see what we can figure out, and we'll do this by proving the much celebrated Riesz representation theorem. So anytime you hear a representation theorem, like something called the representation theorem, whether it's a Riesz representation, the Markov-Kakutani representation theorem, whatever else, what it means normally is that it's saying that all functions of some type can be written in a particular form, can be represented in some convenient to work with way. In the case of the Riesz representation theorem, it is all about the linear functionals on finite dimensional vector spaces. So the claim is that if V is a finite dimensional vector space, and I'm going to super underline that because that is extremely important. Finite dimensional matters a lot here. And phi is any old linear functional on V. So this says phi is in V prime. Then there's a unique vector, kind of cool, V and V, such that phi of u is equal to the inner product of u with V for every u in u. That is, you can write everything in the dual space as an inner product. Every single thing. That's nuts. So to answer our question here about, integrate against cosine or something like that, and I'll even put parentheses around cosine just to make it look nice. This, you can check, very routine to check, is indeed a linear functional. But if I pick some inner product on Pn, the polynomials of degree at most n, I can, apparently, according to the Riesz representation theorem, always write this as an inner product with a fixed element, with a fixed polynomial. This is actually crazy if you consider this example. That doesn't seem like it should be the case at all. Let's prove it. Let's see how it works. Then we'll do a great example using this exact one. So the proof of this bad boy is kind of fun because it's not actually too hard. It's much less involved than some of the other things we've been proving in recent sections. And in fact, I think looks pretty clean. So the idea is as follows. Let's let E1 through En be an orthonormal basis of V. Last time we proved that every finite dimensional vector space with an inner product on it has an orthonormal basis with respect to that inner product. All you got to do is take a regular old basis for V and then use the Gram-Schmidt procedure on it. So you just take it and you orthonormalize it. You subtract off the parts that aren't orthogonal, just going down the list, and then you divide by the length of everything you got. Not too bad. Okay, so got an orthonormal basis. Then, here's the nice thing. If phi is in V prime, we get the following. Phi of u is equal to phi of, check this out, u, E1 times E1 plus ... all the way down through u inner product with En, scaling En. And this is because you can write u in this form. It's not a parenthesis, that's a inner product bracket. We proved this last time or the time before you. No, last time. Yeah, we proved this at the start of class last time. So we showed, hey, if you've got an orthonormal basis, then you can write any vector as a linear combination of those basis elements really easily because the coefficients are just the inner product of the vector with the corresponding basis element. Okay. Now via linearity, you can break this apart quite simply. So these are just scalars. I'll pull them out. Okay. So this is via linearity. The linearity of phi, the linear functional right here. All right, nothing too bad, nothing too terrible yet. But now, why don't I just take these phi e1 down through phi en, which are, notice, just in the field. They're just scalars. And why don't I just bring them on in? That is, would you agree with this? So this just follows from the fact that x lambda y, or x inner product with lambda y is equal to lambda bar inner product of xy. So this is one of the nice properties of an inner product. That is, in the second slot, you can't exactly just pull out scalars, but when you pull them out, if you conjugate them, then everything works fine. So if we do it the other way, pull it inside, all we have to do is conjugate, since the conjugate of a conjugate is itself. Yeah? That is, all of these guys I could rewrite, if you like, as a conjugate of a conjugate. It looks kind of confusing to do that, but it just lets you clearly see how we're pulling this back inside. So from here, I'll just use additivity in the second slot yet again. I'll get u 5e1 bar e1 plus dot 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 all the way down through phi of en bar en. That is, all I'm doing is I'm applying my linear functional to my dual, or to the elements of this orthonormal basis, and then I'm conjugating it. And then I'm just using that as the coefficient next to the corresponding dual basis element. And bada boom, this is equal to uv for v equal to phi e1 conjugate e1 plus dot 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 all the way down to the conjugate of phi applied to en, scaling en. And let me add some justification for that part. So this is via additivity in the second slot, or second argument, I guess you could say, of the inner product. And bada boom, there you go. Okay. So there does exist some v in v such that phi u is equal to u inner product with this v for all u in u. To be clear, why we can see that this works for all u in u is, check it out. This v doesn't even remotely depend on u. It's all in terms of the orthonormal basis. And it works no matter which orthonormal basis you choose. Pick any one you want. You'll get a v. Bada boom. Okay, now we have one other piece right here. So we said that there is a vector such that this happens. But we got a big claim here, uniqueness. Okay. For uniqueness, suppose that v1 and v2 in v are both such that phi of u equals u v1 and phi of u equals u v2. Then 0 is certainly equal to phi of u minus phi of u, which is then equal to u v1 inner product minus inner product of u with v2, which is just equal to the inner product of u with v1 minus v2. So taking u equal to v1 minus v2, we get 0 is equal to v1 minus v2, inner product with v1 minus v2, which we know is the norm of v1 minus v2 squared. But what's the only vector in any inner product space that has norm 0? That's right, it's the 0 vector. Hence, v1 minus v2 is equal to 0, which is just a fancy way of saying that v1 is equal to v2. So, this vector is unique. And we're done. That is, we found a vector and we said, hey, suppose there are two such options. We showed that really it's actually the same option. There was only one way to do this in the first place. The Riesz representation theorem, guys. How about it? If V is finite dimensional, which notice we need to get a basis, right? Otherwise, we don't have a basis and this whole trick falls apart. Oh, okay. So for V finite dimensional, every linear functional on V is an inner product. At least, I guess for V, a finite dimensional inner product space. Then every linear functional is an inner product with a fixed element. That's what I'm trying to say. So let's revisit this confusing example right here. This one about cosine, which is not a polynomial. And let's see what goes on. Let's try it out. Okay, here's the example. And this is a fun one, I think. So, is there a polynomial such that the integral, let's say from -1 to 1, that you could pick any other upper and lower bound that you feel like, of p of t times cosine of t dt is equal to the integral from -1 to 1 of p of t q of t dt. So let's say a polynomial q of t such that this holds for all p in, say, how about p2 of r? On first glance, this seems strange to imagine, since cosine of t is not a polynomial. Nonetheless, there is. Amazing! It's an exclamation point. Nonetheless, there is. Here's how. So, define an inner product on P2R, or really I could just say Pn, it doesn't really matter, via PQ is equal to the integral from -1 to 1 of P of t Q of t dt. Okay, if you don't believe this is an inner product, check it really quick, but I claim it's not too bad to see. Namely, you can, since we're over the reals, we don't have to worry about any conjugation business or anything like that. Notice you can pull scalars out from either one of these, just pull them outside the integral. And since you can split up integrals across sums, we got additivity in each slot. Okay, looking pretty good. Check the rest of the things in the list of criteria we need for an inner product, and you'll find that everything works out. If you don't believe it, pause the video and double check for yourself. It's a great exercise. But take my word for it for now. if you don't want to, I guess. I mean, you should double check if you don't believe it. But let's proceed without going through the long and arduous process of actually verifying it. Just trust me, it is indeed an inner product. Okay, then here's what we'll do. Since phi of p is equal to minus 1 to 1 of p of t cosine of t dt is a linear functional on P2R. Again, something that you should check. The Rees-Rep theorem, the Rees representation theorem, says the following. Says that there does exist Q in P2R such that phi of P equals PQ inner product. Okay, what is it? Well, we'll need to get an orthonormal basis. Let's use an orthonormal basis for this one. So we'll have to come up with one. Let me grab one really quick for us. Well, okay, I was going to grab one for you and just write it down really fast. But actually, now that I think of it, I paused the video really quick so I could remind myself of the exact calculations. Let's actually just derive one. So, to get it, we need an ONB, orthonormal basis, of P2R. Call it E1, E2. What dimension is P2? I would say that it's dimension 3, right? So we can construct V is equal to, looking back at our proof over here, well, the V is going to be the linear functional applied to E1, conjugate E1, plus all the way down through linear functional applied to En, conjugate En. Except here, we don't really have to care about conjugation or nothing, since we are living in the world of the reals. But I'll still write it that way just to be clear for notes. Okay, so maybe I shouldn't call this V actually. Let me call this Q, just to be clear. So this will be the thing that does it. Since, watch this, PQ would then be equal to P inner product, wrong side for the brackets, P inner product with phi E1 bar E1 plus phi E2 bar E2 plus phi E3 bar E3 inner product. Okay, and all we have to do now is to put everything together. And this part is not actually too bad. We just break it apart in the opposite way. I'm just reminding everybody of why this will be true. So I've got a P E1 times phi E1 plus P inner product with E2 times phi E2 plus P inner product with E3 times phi E3. And now all I have to do is just put it right back together. And don't you know it? What am I going to get? Well, all I got to do is just figure out, looking back right over here, how to bring it back into the first slot. That is, bring it all back into phi. So, going back on over, now all I got to do is put this back together to get phi of P E1 plus inner product of P with E2 plus inner product of P with E3 oops, that's not an angle bracket, that's a round bracket. And just notice that this is actually just phi of P. Okay, so all we need is this orthonormal basis, and then we know exactly how to build Q. And in fact, you can verify that Q works just on a purely symbolic level without even knowing what it is. So let's build this orthonormal basis. To get this OMB, or any OMB really, I guess, let's start with the basis. Let's say V1 is equal to 1, V2 is equal to x, and V3 is equal to x squared. Then apply the Gram-Schmidt process. Okay, so all we got to do is first take F1 to be V1, which is just 1. Thus, the norm of F1 squared is just the integral from -1 to 1 of 1 dt, which is 2. Okay, so F2 is equal to V2 minus the inner product of V2 with F1 over the norm of F1 squared, scaling F1, which is equal to x minus inner product of x with the constant polynomial 1 over the norm of F1 squared, which is 2, which, hey, would you believe it? What is the inner product of x and 1 right here? This is x minus, well, we're going to integrate from -1 to 1. I'll just write it as t dt. T times 1. Maybe I'll even make it super clear, just so when you're looking back. Over 2. And f1 right here is just the constant function 1. But hey, wouldn't you know it, this is 0, so we can get rid of that whole business right there, and we just get back x. So f2 is indeed x. Okay. So norm of f2 squared, well, this is equal to the inner product from -1 to 1 of, well, let's see, it's just going to be t dt, since f2 is equal to x. And all this is, all you have to do is do a little tiny bit of calc 1, is 2/3. So writing f3 now, f3 is equal to, well, v3 minus the inner product of v3 with f1 over norm f1 squared minus the inner product of v3 with f2 over norm f2 squared, f2. Let's write out what it is. It's x squared minus, let's see really quick. So this will be inner product of x squared with 1 over 2 times the constant function 1 minus the inner product of x squared with, let's be careful here, with x over 2/3 times x. Okay, and now all I have to do is simplify this out, and if you go through and you do the integrations that you need right here, I promise you, you'll get back x squared minus 1/3. Huh. Hence, now all we have to do is find the norm of f3 squared, which is equal to, notice, the integral from -1 to 1 of t squared minus 1/3. Did I make a... Oh, when I squared this, the norm of f1 squared. Sorry, I should have put a squared here. My apologies, guys. And I mean the same here, but it's the same thing. So, I mean, it's still 1. That might have confused people. I forgot to write the 2, and so you would not get 2/3 there. You would, in fact, get 0 in that case. Sorry about that. But this is squared dt. Oh, man, I hope that didn't throw anyone off. I mean, it probably did, but hopefully now that we're talking about it, it doesn't throw anyone off too bad. Sorry about that. I just forgot to write the 2 right there. We have to write it here. All we're doing is we're just proceeding, to be clear, using the inner product given here. And when we take norm squared, you're just taking the inner product of a thing with itself. So you're integrating its square over the interval from -1 to 1. So I just got a little bit too sloppy right there, since when you write 1 and you square it, it kind of is automatic to just leave it as 1. I forgot to write the square here on t. But anyways, when you integrate this guy squared dt, if you believe me, this is in fact 8/45. Okay, so the list E1, E2, E3 with EI equal to FI divided by its norm is just, or is an orthonormal basis. And E1 is equal to the square root of 1/2. E2 is equal to the square root of 3/2 times x. And E3 is equal to the square root of 45/8 times x squared minus 1/3. There you go. Okay, so we've got an orthonormal basis. We just did Gram-Schmidt. All we did is we started out by taking f1 equal to our first basis element. Then we found its norm. Okay, not too bad. Cool. Then we could find f2 by taking v2 and subtracting off the piece of v2 that is not orthogonal to f1. Okay, cool. Then we can find f3 by taking v3 and subtracting off the part of f3 that's not, or the part of v3 that's not orthogonal to f1 and the part of v3 that's not orthogonal to f2. And we're left with only the part of f3 that's orthogonal to both f1 and f2. Nice. Then just normalizing, dividing by the norm, we're set to go. Cool. So let's use this list right here and go back to what we were talking about before. The polynomial q of x given as follows, which is, and I will write it out in its gory detail, it's the integral from -1 to 1 of the square root of 1/2 times cosine of pi t dt. Did I do this as cosine of pi t, or did I just do cosine of pi? Oh, I wrote cosine of t. Let me make it cosine of pi t. I already have that calculated out. Sorry, guys. It is a Monday, isn't it? I've made 2 small mistakes right here. And I'll just change this to pi t. Sorry, guys. Okay. So the only thing I did is I said cosine of t instead of cosine of pi t. We can do cosine of t if you want. I just did not already calculate out what things should be. So here, let me just change all the occurrences of cosine to cosine of pi t just to make our lives a little bit easier. Okay, so if you're all right with me just doing that, and if you want to do it with cosine of t instead of cosine of pi t, it's not hard. Just erase all of the pi's in the formula I'm about to write, and then you're good to go. But hopefully this is a little bit clearer. So I'm taking E1, or I'll just write out the formula. So, and then I'll annotate it with some colors. So integral from -1 to 1 of square root of 1/2 times cosine of pi t dt, and that's scaling the square root of 1/2, plus the integral from -1 to 1 of root 3/2 times t cosine of pi t dt, and that whole thing is going to be scaling root 3 over 2 times x. And then finally, I will add on, and I might have to write this on the next line here, plus the integral from -1 to 1 of, and now I'll just put in 45 over 8 in the square root, and then t squared minus 1/3 times cosine of pi t, and this whole messy thing right here, dt, and this is going to be scaling root 45 over 8 times x squared minus 1/3. And if you want to see what each piece of this is E1 and E1, E2, E2, E3, and E3. That is, what I have right here is, in particular, this whole thing is phi of E1 times E1 right there. Now I have phi of E2 times E2 and phi of E3 times E3. Since I am working over the reals, I might as well write these as conjugates just to make it clear that I am doing precisely the formula I said back over here. Take the conjugate of the functional applied to each of our elements in our orthonormal basis and use those as the scalars in a linear combination of the elements in our orthonormal basis. And from this, what we get out is the following. Just writing this vertically right here. Sorry, I had to write that on 2 lines. It's kind of a long formula. You get out 15 over 2 pi squared times 1 minus 3x squared. Whoa. That is the polynomial. And if you want to see that this is indeed true, check this out. So I went ahead and I put all of this into a graphing calculator right here. You can see what these polynomials look like. Here, I will take this and I will get rid of that really quick. Okay, so here's the idea of it. I'm going to take this one, move it down. Okay, I picked a random polynomial of degree 2. 2t squared plus t minus 1. All right, that's graphed in blue right here. Cool. Here's q1, or q as I said it. I'm calling it q1, but let me just call it q for the moment. I will talk about the q1 versus q2 when I generalize this. And look at that. I took the integral of p with cosine of pi of x dx on the interval from -1 to 1, and I got back negative 0.810569469,139. Okay, and if I do the same thing with q and p, I get back the exact same value. This is kind of nutso, actually. So if I want to really drive the point home, let me just say graph cosine of pi x really quick right here. I wish it would do it in a different color. It's an unfortunate choice. Okay, so here's p, here's q. So let me graph just really quick. I'll put p of x cosine of pi x. And then I'll even also do p of x, q of x. And look, they're kind of similar, but they're not really that similar. If you look over the interval -1 to 1, they're actually like a little bit off from each other. But the amazing thing is that over the interval -1 to 1, the places where the green one is higher than the blue one are counteracted by the places where the green one is lower than the blue one. That is, those two things balance each other out. So you end up getting that the integrals are the same. That is crazy. And we can switch what p is really quick, like put it like 7 or 4 or 11 or 56. It looks really messy when I do that. I'd have to zoom way the heck out. But I could put like -2, and I could even get rid of the constant term. And like, hey, yet again, we're just getting something that looks pretty similar where the places where green is above blue are balanced out by places where blue is above green relative to the sign change over the interval -1 to 1. Okay, now just going back really quick, what about if I do this over something else? So here, let me go on to the next page really fast. Okay. Example. What about if we want to do this for a polynomial of a different degree? All we have to do is repeat this process with an orthonormal basis of PNR, where n is our desired degree. Oh, wow, okay. For example, if n is equal to 5, then, and believe me here, the polynomial, I will write it out, q of x is equal to, this is a big boy, 105 over 8 pi to the 4th times this terrible quantity, 27 minus 2 pi squared plus 24 pi squared minus 270 x squared plus 315 minus 30 pi squared times x to the 4th satisfies integral from -1 to 1 of p of t cosine of pi t dt is equal to the integral from -1 to 1 of p of t q of t dt for all p in the polynomials of degree 5 with real coefficients. And if you want to see that, I went ahead and I popped this back on in the graphing calculator here, and let me instead now use this q. So I will, instead of using the first q, or actually taking my first q and calling it now q1, just for convenience. Okay. And I'll even graph p of x, q2 of x now. Oop, too many parentheses. There we go. And I'll call this q1 now. Bada boom. q2. Okay, cool. And I'll put that q2 up here. Okay, now looking down over here. Oh, maybe I've made this a little bit too shoved in the corner there. Sorry if it is. I'm cutting off the beginning of things. Sorry about that. All right, here we go. Okay, there we go. Sorry if I was cutting off some stuff over there before. Okay, let me make this a little taller so you can see everything all at once. Nice. Okay, and actually let me take this and let me get rid of the grid lines. Yeah, that's fine. Bam. Maybe that looks cleaner. Okay, so over the interval from -1 to 1, I think I made this guy pretty big. Okay, so over this little interval right here, this guy does get kind of crazy between -1 and 1. But my whole point is just that, hey, look, you got your p of x times cosine pi of x. That's the thing we actually want in orange. If you do q1, you get this pink line, and if you do q2, you get this white line. And hey, would you look at that? You get exactly the same answer for every single one of these integrals, since a polynomial of degree 2 is certainly also a polynomial of degree at most 5, as well as a polynomial of degree at most 2. But now if I switch it to, say, a degree 3 polynomial, it will work because we're on a interval that's symmetric about 0. But if I go to a degree 4 polynomial, check this out. Basically, I just want to make sure I don't have an odd function. But check this out. Look at this. Over the interval from -1 to 1, well, a t to the 4th minus 2t plus 1, that is definitely not going to be an odd function. So if you look, check it out. P of x cosine pi of x, its integral over -1 to 1 is minus 0.13780 some other stuff. But if I do it with q1, I get something that is slightly off. I get 0.34738 and some other stuff. But if I do it with q2, I get exactly the right answer. So for polynomials of degree up to 2, you can use q1 and get the exact same thing as if you use q2. But if you want to go up to degree 5, you got to use q2. And as soon as you go to, say, degree 6, now we're actually off for both q1 and q2 when we integrate. In both of these cases, we are not getting the right answer. We're off by a little bit. In the case of q2, we're off by less than in the case of q1, but we're still off. So this is a really useful thing. If you're doing any kind of like applied mathematics, being able to replace a function that is not a polynomial with one that is in some restricted setting, that is for polynomials of up to a certain degree when calculating an integral like this, oh my goodness, that is so nice and easy. It can save you a ton of time having to try to approximate an integral when you can actually just directly, algebraically, by hand even if you want, produce a formula that gives you the answer. So, really useful, a really good trick that will help a lot if you do any kind of applied mathematics. And it's just generally actually kind of a neat little thing to do at parties, I guess, if you have a lot of time to, write on a whiteboard at a party. So there you go. A good example of how the Riesz representation theorem can take something that otherwise might be difficult to calculate and in a restricted setting, turn it into something that is easy enough that you can calculate it by hand. Really cool. So I'll leave it there and I'll see you next time. Have a good one.